Okay, I'm now going to go through part B of the mid-year exam for year 12. So it starts with that data analysis question. The student carries out an experiment to investigate how rate of flow through a narrow tube varies with the pressure difference across the tube. The pressure difference is proportional to the height h as shown. The student measures h in centimeters with a meter ruler. R is obtained by measuring the volume of water collected in a measuring cylinder in a time of 100 seconds. So what the student has done is taken as the independent variable this height, h, and so for one experiment he or she has kept the height constant, so kept the height at that level, and with the water level maintained at that height, measured how much volume is collected here over a time of 100 seconds. So the measurements made is the height, the time, and the volume. Okay, let's have a look. Here's the data. The student enters the data on a spreadsheet and produces the graph shown below. Okay. The data point for h equals 57 centimeters, r equals 1.7 has not been shown on the graph. The student estimates the uncertainties to be plus or minus 1 centimeter for h and r to be 5%. Okay, so the first thing we need to do is draw the missing data point. Okay, so it's going to be at h equals 57. So 57 is here. And r equals 1.7. So each of these is 0.01, sorry, no, 0.1. So there is 1.57. So if we go across there all the way to here, that's where our point is. And then we want the vertical error bars. Well, the uncertainties in the values of r is plus or minus 5%. So let's figure out what 5% of 1.7 is. So 0.05 times 1.7 is 0.085. Well, that's slightly less than 1 square, because 1 square is 0.1. And so our error bars should be just ever so slightly smaller. This is very hard to draw on the smartboard. Than 1 square either side. Okay. Comment on why the trend line is not a perfect match for the data. Well, we have at least one point that falls off of the line, this one here. And this point here is not great either. So not all of the trend line does not go through the error bars for all points. So we can say the trend line does not go through all, error bars of all data points. And that was only one mark. Okay. Explain why the student's estimate of a 5% uncertainty in all values for r is unlikely to be correct. Okay, so the way that the student measured r is to take the volume divided by the time, which was 100. Right? The measurement in the time, so uncertainty here is constant. The uncertainty in the volume, the absolute uncertainty in the volume, because he's using the same measuring cylinder throughout the experiment. So whether he or she is measuring a small volume or a large volume, the absolute uncertainty should be the same because it's got the same tick marks. It might be like plus or minus a milliliter or whatever. So the absolute uncertainty in the rate, so absolute uncertainty in R depends on absolute uncertainty in V and T, neither of which changes in the course of the experiment. Right? So this means that if the percentage uncertainty stayed the same as the volumes increase, that would mean that the absolute uncertainty in the volume is increasing. So a constant relative uncertainty would imply or implies that the absolute uncertainty in R increases or does increase as R increases. Because 5% of a bigger R would correspond to a bigger absolute uncertainty, then that clearly isn't happening by the method that the experimenter is making the measurements. Right, so that's kind of a tricky question, and it really requires a good understanding of how relative uncertainties and absolute uncertainties relate to one another. B, the student estimates that the uncertainty in timing is plus or minus 1 second. Using the data on the graph, deduce the absolute uncertainty in the volume of water collected when R is 2.1 centimeters cubed per second. Okay, so we're going to have the relative uncertainty in time is 1 over 100, which is 1%. Relative uncertainty in R, we were told, was estimated at 5%. So that's 5 over 100, which is 5%. Okay, volume is equal to the rate of flow times the time. And so the relative uncertainty in the final volume, well, let's just calculate what the value is first. So R is 2.1, and the time was always 100. So that's 210. And because we're multiplying, we're going to add the relative uncertainties. So it's 210 plus or minus 1%. Okay, the absolute, so not 1%, what am I thinking? Let's fix that. It is plus or minus 1% plus 5%, which is 6%. Because when we multiply values, we're going to add the relative uncertainties. Okay, but we wanted what we wanted was the absolute uncertainty. And so the absolute uncertainty is just going to be equal to 0.06, or in other words, 6% of 210 times 210, which is equal to, well, it's going to be 6 plus 0.6, which is 12.6. and the units for the absolute uncertainty is the same as the units for V, which is centimeters cubed. Okay. This question is about gravitation and uniform circular motion. Phobos, a moon of Mars, has an orbital period of 7.7 hours and an orbital radius of 9.4 times 10 to the 3 kilometers. Outline why Phobos moves with uniform circular motion. Okay, so the first point to make here is that the period is constant, so we can assume that the period is constant. We can assume that the radius is constant. So assuming radius of orbit is constant, the path is circular. Okay, that's one point that we could make. Another point that we should really make is that the net force is equal to the gravitational force between Phobos and Mars, which at all times is directed towards the center of the orbit. In other words, it's centripetal. Maybe we should write that just in case they want that keyword. I.e. centripetal. Therefore, A, acceleration, is towards center, while V is tangential. Okay, that should be enough to get us the 3 marks. You can double check on the mark scheme. Alright, the next question says, show that the orbital speed of Phobos is about 2 kilometers per second. I'm going to scroll down just so I can see, can I fit both the information and the question? Yes, I can. Okay, so it says here, show that the orbital speed of Phobos is about 2 kilometers per second. So the orbital speed is equal to the circumference, so 2 pi r, divided by the period t. So that's 2 pi times 9.4 times 10 to the 3 divided by the period, which is 7.7 hours. But we want it in meters per second, our answer. So it's 7.7 times, so there are 60 minutes in an hour, and then there are 60 seconds in a minute. And so our final answer will be 2 times pi times, what was the radius? It was 9.4 times 10 to the 3 kilometers, so 9.4 times 10 to the 6 it should be. 9.4 times 10 to the 6. And then we're going to divide that by 7.7 times 60 times 60. Close bracket equals 2,130. 2, 1, or 2, in fact, let's just write 2.1 times 10 to the 3 meters. Okay, and I'll just correct this mistake that I made in my working here. Which is that was actually 10 to the 6 because it was 9.4 times 10 to the 3 kilometers. Okay. The last one is deduce the mass of Mars. Okay, so we know that the net force is provided by gravity, and the mass of Mars is going to feature in this gravity equation. So we know that the net force mv squared over r, the centripetal force, is equal to the gravitational force, which is g big M over r squared times little m, sorry. Okay, but we can cancel these m's, so let's do that. Cancel and cancel. And then we'll just rearrange this for big M. In fact, we can cancel one of the r's here as well. We'll cancel that with that. Okay, and then we rearrange this for m, and we get m is equal to, we're going to multiply up the r and divide the g, so we get r times v squared over g, which is equal to 9.4 times 10 to the 6 times v squared, which was 2.1 times 10 to the 3. You really should use the unrounded value here. I'm not going to because I haven't written it down. Divided by 6.67 times 10 to the negative 11, the universal gravitational constant, which is provided in your data booklet, by the way. And that is equal to, let's figure it out. So it's 9.4 times 10 to the 6 times 2.1. Actually, I'll start again. So 9.4 times 10 to the 6 times 2.1 times 10 to the 3 squared divided by 6.67 times 10 to the negative 11 gives us, whoa, okay, what's that? 3, 6, 9, 12, 15, 18, 21, 4.23 times 10 to the 23.